Physicists learned a lot about electricity and magnetism in the 19th century. We already talked about one of the biggest discoveries: that electric current can create magnetic fields. And once scientists had figured it out, they wondered if the opposite was also true. Could magnetic fields create or induce an electric current? Many physicists designed experiments to detect electric currents induced by magnetic fields, but they kept coming up empty. That is until two physicists, Joseph Henry and Michael Faraday, both on their own figured out what was happening. It turns out that magnetic fields do induce electric currents, but only under certain circumstances, when the magnetic field is changing with time. And this discovery is what eventually led to the creation of hard drives as we know them today. When Faraday discovered that magnetic fields induced electric currents, he got kind of lucky. He set up a current flowing through a coil of wire so that it would generate a magnetic field, and then he watched to see if the magnetic field induced a current in a second coil of wire. And well, nothing happened. That must have been pretty disappointing at first. But then, weirdly enough, Faraday noticed that when he turned the current on and off in the first coil, there was a brief spike of current in the second coil, but only while the current was changing from off to on and back again. He realized that he'd been looking for the wrong thing. A constant magnetic field didn't cause an electric current in a loop of wire. Only a changing magnetic field did. These days we call this idea Faraday's law of induction. It says that changing magnetic fields will induce an MFA in a loop of wire. An MFA, you recall, stands for electromotive force, which is what causes electrons to move and form a current. So now Faraday knew that when a magnetic field changed over time, it induced an MFA in a loop of wire. But a couple of other things induced MFA too, even if the strength of the magnetic field stayed the same. Changing the area of the loop of wire induced a current too, and so did changing the angle between the loop and magnetic field. That's because of a property that most directly induces MFA, the property known as magnetic flux, represented by phi-v. Magnetic flux is essentially a measure of magnetic field running through a loop of wire, and when that field changes. That's what induces an MFA, and there are three factors that affect magnetic fields, and therefore the magnetic flux through the loop. First is the strength of magnetic field, which we label as B. Next is the area of the loop, A. If the loop is bigger, there would be a larger magnetic field running through it, and vice versa. And finally, there's the angle of theta between the magnetic field and the line perpendicular to the face of the loop. Combining all the factors, we find the magnetic flux is equal to the strength of the magnetic field times the area of the loops, times the cosine of the angle between the magnetic field and the perpendicular line. And if the magnetic field and the loop are perpendicular, then the magnetic flux will be just equal to the strength of the magnetic field times the area of the loop.
Magnetic flux is measured in units of Tm squared, also known as Webers. But when it comes to inducing EMF, what really matters is how the flux is changing over time. If the magnetic flux through a loop of wire decreases over time, the EMF increases accordingly. And if the flux increases over time, the EMF decreases. In math terms, we'd say that the EMF is equal to the negative of the change in flux over the change in time. This equation works well for the change in flux through one loop of wire, but often you'll be inducing EMF in a coil of wire, like what Faraday was doing in his experiment, so it helps to know how a change in the magnetic flux will induce EMF in a coil. And the key here is that a change in the magnetic flux through a coil induces the same EMF in each loop of the coil. So if you want to know the total EMF in the coil, you calculate the EMF for one loop of wire, then multiply it by the number of loops in the coil, or N, which means that the induced EMF in a coil of wire is equal to the number of coils, times the change in magnetic flux over the change in time, all multiplied by a negative sign. So having two loops in the coil would mean double the EMF that would be induced in one loop, while 10 loops would mean 10 times the EMF. So Faraday's law of induction lets us calculate how much EMF and therefore how much current will be induced in a loop of wire by changing it in magnetic flux. But in what direction will the induced current flow? To figure that out, we use a rule called Lenz's law, but for this video that's all.